So chapter 8 is about estimating single population parameters. We will be talking about two types of parameters. We will be estimating the population mean, and we will be estimating population proportion. In chapter 7, we did a great job in terms of making connections between population distribution and sampling distribution, and we come up with a very important idea that we can estimate the mean of the sampling distribution to be the population distribution, to be the population mean. And the same is applicable with the population's proportion and the population or the sampling distribution the proportion. And also we talked about the standard deviation of the sampling distribution, which is equal to the standard deviation of the population divided by a square root of the sample. Why this is important? Because we can study the sampling distributions. If you study the sampling distribution, then you can make some estimations for the population parameters. So we will be talking about the point and confidence interval estimates. We will be determining the required sample size for estimating the population mean, and we will be estimating the population proportion. And the idea is to estimate the population mean and the proportion. Because we have access to the sample, we don't have access to the population. So we will be trying to use the data we got from the sample to tell something about the population's parameter. We have two types of estimates we can create, we can make. The first one is a point estimate. And what is the point estimate? Is a statistic. It's a measurement taken from the sample, and it's used to estimate the corresponding population parameter. And the point estimate of the population's mean is going to be the sample mean. Is going to be the sample mean. The point estimate of the population mean is going to be the sample mean, and this is kind of the point estimate for the population mean. The second type of estimate is going to be the confidence interval. What is the confidence interval? Is the interval developed from sample values such that if all possible intervals of a given width are constructed, a percentage of these intervals known as the confidence level will include the true population parameter. The confidence interval is an interval. It has a lower confidence limit and it has an upper confidence limit, and the middle of this interval is going to be the point estimate. Example. Let's just study this example. The Health Star Energy Drink Company makes and markets a popular energy-enhancing drink. The company has installed a new machine that automatically fills the energy drink bottles. The machine allows the operator to adjust the mean fill quantity. However, no matter what the mean setting, the actual volume of the energy drink liquid will vary from bottle to bottle. The machine has been carefully tested and is known to fill bottles within an amount of liquid that has a standard deviation of 0.2 ounces. So they tested the machines. There's kind of some variation to bottle. The variation is about 0.2 ounces. The filling machine has been adjusted to fill cans at an average of 12 ounces. So this is the adjustment of the machine. This is the average of the population. I mean, this is the target average. So we are adjusting the machine in a way that the machine has to give you to fill in bottles with 12 ounces or an average of 12 ounces. So that means if you take, for example, thousands, or if you, let's say, have the chance to collect all of the bottles and calculate the average, it should be 12 ounces. This is the target population mean. So this is my mu. This is our target population mean. After running the machine for several hours, a manager selects a random sample of 100 bottles. Because you can't basically access all of the population, you cannot count all of the populations, or you cannot measure the liquid in each bottle, so that's why we have to take some samples. So the manager took a sample of 100 bottles and measures the volume of the liquid in each bottle in the company's quality lab. After that, he creates a histogram of the data, and the distribution is centered at a point larger than 12 ounces. So the manager wishes to use the sample data to estimate the mean fill amount for all bottles filled by this machine. So he took 100, right? Then he counted, or he measured the volume in each, and he found these measurements. This is only one sample. This is important. This is only one sample of 100. So it's one sample, and he found that the average is higher than 12. It's a 12 point something. So the sample mean computed was 12.79. This sample mean is, we call it unbiased point estimate of the population mean. So the first question, if I ask, what is the point estimate of the population mean? Someone is going to ask me, do we know the population mean? No, we don't know the population mean. The 12 ounces is our target. So what did we do? We took a sample of 100, then we found the average. We got 12.79. Then we can call this one that this is the point estimate of the population mean. So this is 12.79. But there's a problem that the point estimate is not enough because the population mean can be larger than this number or smaller than that number, right? It could be larger than this or smaller than this one. So to make a better prediction or estimation, to make a better estimation for the population mean, we have to develop what is so-called confidence interval. We have to do the confidence interval estimate for mu. Give me an interval. Give me upper limit and lower limit for that population mean, because this one is not actually accurate. To calculate the confidence interval, we are going to follow some steps. However, we have to, first of all, to distinguish between two scenarios or two cases. The first case, we have to make sure that, number one, if the simple random sample, the one we took, it's taken from normal distribution, is the first scenario, right? If the simple random sample is taken from a normal distribution population, so this is a normal distribution of the population, or if the population itself is not normally distributed. So if the population is normally distributed, then the sample is taken from a normally distributed population. If the population is not normally distributed, we have to make sure that the sample is really large enough. So we are able to use the central limit theorem, the one that we explained in detail in chapter 7. So to give the confidence interval, it's going to be confidence interval. The confidence interval, it's going to be what? The point estimate because the point estimate is not that accurate, and we said the population's mean can be greater than this point estimate or can be less than this point estimate. So either we add or subtract some kind of error. So we're going to call it margin of error. Later, we're going to call it little e. What is the point estimate of the population mean? It's x bar, which is the sample mean, plus or minus. What is the margin of error? It's going to be something we call the critical value, the z value, times standard error. The standard error. So this is, let me first. The point estimate of the population mean is the sample mean plus or minus the critical value. We will be talking about this critical value times standard error. What is the sample mean? It's x bar. What is the critical value? It's the z value times the standard error, square root of, it's sigma divided by square root of n. What is sigma? It's the population standard deviation. What is n, little n, is the sample size. So this is going to be my confidence interval, right? And we will be talking about something very important. Sometimes we have access to this, to the population's standard deviation. How do we have access to this? Sometimes we use historical data to get standard deviation of the population. However, is that possible or is that something available? No. Sometimes we don't have access to the historical data. Sometimes we don't know anything about the standard deviation of the population. That's why sometimes we will be using the sample standard deviation. If we use sample standard deviation, we're going to use different distributions. So we'll be discussing two different cases here. The first case when we have access to this guy. The second case when we don't have access to this guy. Okay? So If you have the sampling distribution, for example, this is my sampling distribution. And if you remember, we talked about this. We said my x-axis is going to be my what? My sample means. And these are, for example, some of the, what is so-called the confidence interval. For example, this is my target mean. This is my target mean, right? And this is, for example, suppose I give you x1 is going to be my first, let's say one of the samples. What is the confidence level? The confidence level is this point, x naught, x1, x bar 1, plus or minus the margin of error. This is the margin of error. Okay. If you, for example, look at x3, this is x3, what is the confidence interval of the population? Is x3 bar minus margin of error plus margin of error. So we can get all of this interval that may contain the population's mean. This interval may contain the population mean, and so on. Now, what does it mean by 95%? Okay, how did we get the 1.96? We got 1.96 from the 95%. The 95%, we call it the confidence level. This is the confidence level. What does it mean by the confidence level? This is a very important concept. It means, let me just put in that simple context so you understand. If you were to take 100 different samples and you compute 95% confidence interval for each sample, look, for each sample, then approximately 95 out of the 100 confidence intervals will contain the true mean value. If you take 100 different samples. So suppose now we're talking about this and this different sample, this is different sample, this is different sample. Where's the others? So 95, if we take 100, 95 of these will contain the true population mean. This is the meaning of we have 95 confidence level, which is good. So if you're looking for more, 99, that means if you were to take 100 different samples and you computed 99 confidence level interval for each sample, like this, for each sample, then approximately 99 of these 100 will contain the true population's mean, which is really good. Why do we need to take 100 different samples? Okay, how do we present them? That's why we use the sampling distribution. We use this. Make sense? So as we said, this is the confidence interval. And to get the critical value, I have to give you the confidence level to get the critical value, the z-value, which is basically just the z-value. You use norm.s.n to get the confidence level. So the first scenario we are going to discuss, as I said before, when sigma is known. This is important. So we have access to the population's standard deviation. So let's do the first case now. In the previous example that we did, excuse me, the sample we took is 100. So this is my little n. And our sample mean was 12.79. And the standard deviation is known. It's given to us of the population. And the confidence level is 95%. So let's find the confidence interval. The confidence interval of the population's mean is the point estimate plus or minus the margin of error. What is the point estimate? Is the sample mean in this case. Plus or minus the critical value times standard error. Again, what is the sample means? X bar plus or minus. The critical value is z of the 95% times sigma over radical n. This is equal to x bar, which is 12.79. I'm explaining this in detail, but you can skip all of this and go to the third step, but you have to understand what does it mean by this. So the Z95, I'm going to either use the table or use the Excel. Excel is norm .s.env, or we can use Minitab. I'm going to try to do something on Minitab to show it to you. So let me show it to you. This is the distribution, and we're looking to, this is 95%, 95%, and the goal is to get this value of the z. If this is 95, how much left for the tails? It's 1 minus 95 divided by 2, right? So this is going to be 0.025. This is going to be 0.025. In Excel, we said Excel give you the left-hand side, so it should be the whole area on the left. What is the whole area on the left? This one, the confidence level, plus this one, right, which is 0.025. Then you plug in this into the norm.s.n to get you the answer. So generally speaking, this is going to be all the time 1 plus the confidence level divided by 2. Okay, times sigma is given to us, and square root of 100 equals. Let me do this in Excel. So we got 12.79 plus or minus, this is 1.96 times 0.02, right? So if you add these guys and multiply them, what you get, we got an interval, because the first time we add, the second time we subtract. So 12.79 minus the multiplication of these two numbers, what we get 12.75 ounces, comma, because it's an interval, 12.83. Interval, it's a from 2. It's a from 2, smallest number to the largest number, okay? So this is my confidence interval. So this is my 95% confidence interval. If I were to take 100 different samples, 95 of these intervals will contain the true population's mean. And our target population mean is 12 ounces. And if you look at this, 12 ounces is not here. So in 95 sample, we will not see the population mean in the mid, or the target population mean here. So that means we have a problem. So the manager, the operation manager, they have to adjust the filling equipment because it's out of the adjustment, right? They are putting basically too much energy drinks, so maybe they are losing on average, okay? So this is the explanation that we have just said. And this is an important interpretation. There's no probability here. It tells you about the confidence level. If you, exactly as we said, if you were to produce all of the possible 95 confidence intervals using the mean of each possible samples of the given size from the population, then 95% of these intervals would contain the population mean. This is exactly what we said. Nothing to do with the probability here about the population's mean. And we talked about the margin of error, which is the amount that is added and subtracted from the point estimate. We call it margin of error, okay, to determine the endpoint of the confidence interval. Also, it's a measure of how close we expect the point estimate to be to the population parameter with a specific level of confidence. So the margin of error, which is E, as I said, is just Z times sigma over square root of n, right? This is exactly when sigma is known. The second, let's look at the difference between two things now. The first one, we found it already. The same example, the confidence interval, we just got 12.79 plus or minus 0.04, which is basically we have between 12.75 ounces to 12.83 ounces when we use 95% confidence level. What if he wants to use 80% confidence level? What's going to happen? So again, we just use the formula. We plug in the numbers. This is the confidence level interval. So this is 12.79. The z value of 80%, 0.2 divided by radical 100, which is 10. Then we use the norm.s.env, 1 plus 0.8 divided by 2, 0.02. If you do the calculations, you're going to get two values between 12.76 Oz to 12.81 Oz. What do you notice? When we have 95% confidence level, this was my interval. This was my interval between these two values. 12.75, 12.83. This is for 95 confidence level. This is the confidence interval when you have 95 confidence level. What happened when you shrink the confidence level? What happened to the confidence interval? It also shrinks. It also shrinks. So this is the 80% confidence level. It becomes smaller. So if the confidence level is actually why it shrinks. This number is the same number here. What makes the difference is the margin of error. We have smaller margin of error. So this guy becomes smaller. Actually, it's become 0.0256. It was 0.04, now it becomes 0.0256. So the margin of error becomes smaller, right? It becomes smaller. So the question is, which one you're looking for? Which one you would like to use? Because now we understand if the confidence level decreased, the margin of error is reduced. If the confidence level is increased, then the margin of error is increased as well, right? So as a marketing manager or as an operation manager, which one makes difference for you? Do you need to have a higher confidence level, or do you need to get lower margin of error? Which ones you prefer? So that's the thing that makes difference in your industry. If you're a marketing manager or something, you have to decide. Do you want to be having high confidence level with a wider interval that may contain the population's mean? Are you flexible in terms of having wider interval, or you're not? You would like to have really small margin of error. So this is the decision that you have to make, right? Okay. Maybe as a marketing manager or as an operation manager here, you decided to do something else. What is it? Because you know that the confidence interval, it contains two parts. This is a point estimate. Plus minus the margin of error. This is the margin of error. Margin of error contains two parts. The first part is the critical value. This is the critical value. Critical value. This is, let me write that down there. This is the margin of error. The margin of error is a product of two things: the critical value times the standard error. As we said, maybe the manager said, okay, I will not sacrifice, I will not change my critical value, I will not change the confidence level, I want to keep it high, I want to be 95% sure. If you don't want to sacrifice here, however, you are willing to minimizing the margin of error, that's okay. You still have another game. You can do another thing. There's another game that you can play. You can play with a standard error. You can minimize. You can lower this one. How? We have, what is the standard error? Is the sigma over radical n. This is times the critical value is z. You don't want to change the 95. That's okay. Plus minus, this is my x bar, right? But you said, okay, and you have no control over the sigma. Sigma is fixed already. We have it from the historical data. But what can you do is, because you want to, the goal is to lowering the margin of error. At the same time, you don't want to touch the 95%. You want to keep it. So what you did is, guess what? You increase the sample size. You said, okay, instead of having 100 bottles, let's have 400 bottles. Because if you increase the denominator, mathematically speaking, if you increase the denominator, if this number becomes bigger, the whole guy becomes smaller. The whole fraction becomes smaller. So if the whole fraction becomes smaller, you multiply by this value, which is already we did not change, then you're going to get something else. And if you do the math here, now let me erase this quickly. And if you plug in all of these numbers, so the confidence level, the confidence interval is 12.79 plus or minus the norm env dot s dot env 1 plus 95% over 2 times 0.2 divided by the square root of 400. So what we get 12.79 plus minus 0.02. Super nice. So what we get the 95 confidence interval is 12 ounces to 12.81 ounces. If you go back, we have 12.76, 12.81. This is narrower. The margin error, look at the margin error, 0.02. It was 0.04 with the old 95%. When we change it to 80%, it becomes 0.0256. Now what we did, we kept the confidence level as is, but we said, let's have more sample. I can take another 300 bottles. Then we can minimize the margin of error, and still we have a really good confidence level, which is 95%. So 95 out of 100 samples. If I get 100 sample and we create confidence intervals, 95 of them will contain the population's mean, and in this case it's really narrow. And this confirms our finding that, oh, our machine is out of the adjustment, so let's do something else to fix it. This is another example, so I'm going to leave this to you to do it. And after that, we'll be discussing, the first scenario was when we have sigma is known. Sigma is known. Because sigma is known, this is important, last point I'm going to discuss. Sigma is known, we have to make sure that one out of the things happening. Either the population is normal. If the population is not normal, the sample size have to be large. What does it mean by large? Greater than 30. So in the previous example, this was known, but we don't have any information about the population, which is normal or no, but we have a good sample size. That's why we followed that method that we followed. So next video, I'm going to discuss the second scenario, when sigma is unknown.